Good morning, good afternoon, or good evening, depending on where in the world you're joining us from today. Welcome to our webinar covering TiDB versus Amazon Aurora. It's my pleasure to be joined by Matthew Penarosa, Solutions Engineer here at PingCap. Matthew, thanks for joining us.
Of course, anytime, Kyle, anytime.
Awesome. So before we get started, just want to cover a few housekeeping items. So we like to keep our webinars as interactive as possible. So while everybody is on mute or in listen only mode, we encourage you to ask questions throughout the webinar. If we find time or stopping point during the webinar to answer that question, we will do so. Otherwise, we've allotted some time at the end of the webinar for Q&A. And we'll also be throwing up some polls throughout the webinar. So we encourage you to take part in those. And we'll share some of the results. And stick around to the end of the webinar. We've got a special offer for webinar attendees today. So stick with us for the next 30 or so minutes. And thanks for joining us for the ride. Matthew, I will hand things over to you.
Okay, cool. All right. Thank you everyone for coming. My name is Matthew Penarosa. I'm a Solutions Engineer here at PingCap. And today I am here to compare TiDB and Aurora. And the title of my presentation is called How to Overcome the Status Quo in Scale, Reliability, and Cost. Jumping right into it, this is our safe harbor statement. This basically just says that this presentation is provided for general information purposes only. Please don't sue us, a bunch of lawyer stuff. All right, moving on. Starting off, and just to lay the groundwork for the comparison between Aurora and TiDB, I wanted to quickly give an overview of the landscape that these databases are operating in. So there are three major categories of databases. The first type of database was your relational SQL databases. And these databases were generally single instance. They were SQL compliant. They have a row-based storage engine. Examples of these type of databases would be, Aurora, MySQL, Postgres. And some of the key traits of these databases were that, they enforced schema, they were ACID compliance, they supported the SQL language, and they were very low latency because they were they're single instance. Now, there were some limitations though with these SQL databases, particularly in regards to scale and high availability and things like that. And that is what brought about the NoSQL databases. They were an answer to some of those limitations that people experienced, that companies experienced on traditional SQL databases. And these NoSQL databases had document store structures or key value store structures. They would have their own custom query languages. And examples of these type of databases would be your MongoDB, your DynamoDB, your Cassandra. And the key traits of these databases, and I think what they were built for, were scalability, high availability, and very flexible schemas. Now when you're looking at these two traits here between SQL databases and NoSQL databases, where your SQL databases have the ACID transaction support, and your NoSQL databases have that scale and high availability support. A third type of database came around that essentially combined the traits, the best traits of SQL databases and NoSQL databases into a brand new type of database called distributed SQL databases. And these distributed SQL databases, they were inherently multi-node. They are inherently SQL compliant. They had row-based storage engines. Examples of these type of databases would be Spanner and, of course, TiDB. And as I mentioned before, these databases in this new category, they're highly scalable, they're highly available, they enforce schema, and they're ACID compliant. So they kind of combined the traits of both NoSQL and SQL. All right, now that we've laid the groundwork for the database landscape, let's jump into Amazon Aurora. So,
hey, Matthew, real quick, sorry to cut you off, but just want to throw a poll up for the audience real quick. So now that we've covered the different database architectures, just want to get a feel for what type of database architectures you all are using in production today. So sorry to cut you off, Matthew.
No.
But also, while while this is up, I know we've got attendees still streaming in slowly but surely. So just a reminder that if you have any questions throughout the webinar, please don't hesitate to ask those, and we will get them answered as we can.
All right. Well, thank you, Kyle. Appreciate it. Am I good to go?
Yep, you are good to go.
All right. So jumping into Amazon Aurora. Amazon Aurora is Amazon's proprietary flagship relational database with MySQL and Postgres compatibility. And Aurora was essentially a response to a desire to add on a lot of those enterprise features to your MySQL and Postgres instances. And like Postgres and MySQL, by default, it's a single instance ACID compliant database, which has the option to add on a lot of these modern features. And so some of these configurable features are scalability of reads past single instance capabilities through replicas with unified separate endpoints for reads and writes, and with automatic load balancing of the replicas through that single endpoint. High availability through automatic failover to replicas, and automatic asynchronous replication of data across different replicas. So very useful stuff. And it's also, I also note that typically Aurora is actually faster than Postgres and MySQL. So it's a proper upgrade. All right. So how does this all work? A single instance, on the left-hand side, you can see a single instance of Aurora. And the single instance is handling your reads and writes in your application, but this instance actually doesn't store your data. It functions as the compute layer for your queries. It's what your application will interact with. This is where Aurora's distributed storage comes in. It can automatically replicate your data 6 times across and spread it across different AZs. So ensuring that your data is highly available across AZs. But what if we want to ensure high availability, not just of the data, but also of our compute layer? This is where we can add more Aurora instances in different AZs, which can function as read replicas and failover replicas. And you can, so in this way, you can scale out your reads, or just have failover replicas if your primary instance goes down. Now, if you notice here, there is actually only one instance that can handle writes at any given time. So what should you do if you max out the write capabilities of a single cluster? Well, this is where sharding comes in. This is where you would create a separate Aurora cluster and you would divide the data across those two. Okay, now let's talk about Aurora's strengths and weakness. Speed. This is Aurora's biggest strength. It will typically outperform Postgres and MySQL. And because Aurora is a single instance writer, it doesn't have to wait for confirmation from its replicas on different AZs before it can complete a transaction. So it can maintain that same level of performance that you would expect from a single node database without having to wait for network traffic. Scale is where Aurora has some weaknesses. This is not to say you can't scale with Aurora to hundreds of terabytes. Many companies do it, but it's not designed natively to handle this. Aurora tables actually use a B+ tree structure, and which means that as the amount of data increases, the performance will actually gradually decrease. So you won't get that linear scalability that you might hope for. And if you want to scale past a single writer, you have to shard, which means you're essentially making a tool work to do something that it wasn't natively designed to do. But it does do okay on reads, which can be scaled out to up to 15 read replicas on a cluster. On the transaction front, Aurora does very well. It maintains full ACID compliance within a single instance. But otherwise, the replicas will have consistency delays because it does asynchronously replicate to its replicas. So a little caveat there. But Overall, pretty good. For as far as function goes, Aurora does well on all the counts that a typical relational database would do well on, like schema enforcement and SQL semantics. It does, however, suffer with query complexity and schema flexibility, but that's something you would expect from a relational database, so not something we'll hold against Aurora. All right. So let's talk about Aurora's fit. When to use Aurora for your application. Number one, if you're already on MySQL and Postgres and you want like a little bit of extra speed, and you need the same features of MySQL and Postgres, but you want a little bit more of those enterprise features, Aurora is natively compatible with MySQL and Postgres. If there's a need for very fast writes, it's something Aurora is fantastic at. If you have a small to medium data scale and they can fit within a single Aurora cluster, that's a pretty good fit. You have a low to medium throughput, particularly throughput on the writes. When you have a high amount of write throughput, Aurora can have some problems. Or you primarily need to scale your reads. If you're a read-heavy application, Aurora could be a great fit for you. Bad fit use cases. I would say at large data scales where you have to manually shard Aurora, it's typically not the solution you want to start out with, because why go to a solution where you have to shard when you go to a solution where you don't have to shard? It also has some reliability issues, and might not necessarily be inherent to Aurora, but if you have like Plaid, for example, Plaid used to have, they have 300 separate Aurora clusters. The probability of a failure just goes up immensely. It also doesn't have linear scalability, so that's another downside. If you also have limited manpower for maintenance at scale, Aurora forces upgrades. And if you're sharding, you have people for shard management, you need to have people for troubleshooting. And it's also use cases that require full ACID compliance across a lower Aurora cluster. The reason why Aurora is so fast is because it doesn't have to wait for that asynchronous replication to different replicas, but that means that it may not contain or may not fully guarantee consistency across a single cluster. Now, there's probably someone in the audience, or at least I've certainly had this thought, is why can't I have it all? Why isn't there some database that just has everything, every feature, and it's fantastic at everything? Unfortunately, everything's a trade-off, right? Distributed systems, they can't have it all. And that's what the CAP theorem essentially states that distributed systems can only provide 2 out of the 3 guarantees at any given time. And those three guarantees are consistency, availability, and partition tolerance. And where Aurora sits is between the availability and partition tolerance sector. And so you can either be consistent and available with partition tolerance, or have consistency with partition tolerance. Fortunately, you cannot have all 3. All right. So,
Hey, Matthew.
Before you jump forward, we have another poll for the audience. So just a quick one here, if I can find it. So just want to see.
So based on some of the challenges
That you just got, oh, no, that's not it. Sorry.
There we go. So
based on some of the challenges that you had discussed and some of the capabilities, so let us know if you've encountered any of the following bottlenecks with your current database. So even if you're not necessarily using Amazon Aurora, we'd love to hear what challenges you're facing with your database today.
all right. Thank you, Kyle. Jumping into TiDB here. So let's talk about what is TiDB. So TiDB is an open source distributed SQL database built for mission critical large applications at scale. And while TiDB is MySQL compatible, it is a brand new code base. It's not a fork of MySQL or Postgres or anything. And we have over 10,000 adopters, many of which you've probably heard of, like Square, Surtec, Bolt, Flipkart, Capcom, LinkedIn, Plaid, Booking.com. And we're also one of the most popular actually, the most popular distributed database on GitHub and the second most popular database overall. So what are the features of TiDB? So TiDB is primarily a transactional distributed database that combines the key features of relational databases and NoSQL databases, offering native scalability, high availability, and ACID compliance. It uses a multi-master architecture for both reads and writes, while providing a single view of your data to your application and automating internal operations and self-healing. It's fully MySQL wire protocol compatible. So it's a very easy lift if you're on MySQL right now to transition to TiDB. It's fully open source. It's horizontally scalable with no manual sharding and zero downtime. It's also highly available. There's no single point of failure in the entire system with auto failover and self-healing capabilities built in. Before we jump into the underpinning architecture of TiDB, I just want to quickly show a real enterprise production cluster. So this is a production cluster from a very prominent organization that uses TiDB. And this cluster contains over 200 nodes, 518 terabytes of data, and 1.8 trillion records, all contained within a single database, a single view of that data. And this company behind this database migrated thousands of MySQL instances into a few TiDB clusters. This is just one of them. And all of these clusters, including this one, are managed by 2 engineers. And so this is one of the beautiful things about packaging all of the enterprise features into a single database. It becomes very easy for a small team to manage. Now, let's talk about the problem TiDB was created to solve. If you're working with a typical relational database like a MySQL and you need to scale past what a single instance is capable of, you have to shard. To do so, you would create a sharding proxy, which will run queries to the independent MySQL instances that store that particular shard of your data. Now, these different shards would also have secondary replicas which can be used for failovers or as read replicas to scale up reads. Now, this works, but it's all manual. It's not inherent to the system. And in this architecture, you really don't have one database system. You have dozens or hundreds of independent database systems, which all have to be managed or independently. If you want to do an upgrade, you have to do an upgrade on each one of these different instances. With TiDB, you have one singular system, which achieves this through automatic processes. And underneath, there might be tons of different nodes, but it's a single system. It's a single system all managed through a single database and a single layer. And you can operate and manage it like it's a single system. In fact, when you're working with TiDB, you might not even notice that it's not a single instance. All right, so how does this work under the hood? So this is what a TiDB database looks like. There are no single points of failure in the entire system. It has instant automated failover if any node goes down, and it appears like a single node system to database users. Here's our TiDB nodes are our compute nodes, and this is essentially our compute layer. And when you connect to these compute nodes, you connect to a single unified database. It doesn't matter which node you connect to. It doesn't matter if you spin up a brand new node and you connect that node. You connect to a single unified database. You can read and write on every node, and it'll be fully ACID compliant across the cluster. It's MySQL compatible. It's completely stateless. So if one of these goes down, another one of these nodes can take its place without any interruption in the system. It also has a very sophisticated query optimizer, which helps speed up and process your queries. But that layer doesn't actually store your data. Your data is stored on our storage layer. And this is a row-based storage engine, and it's highly available with automatic failover. It automatically stores your data 3 different times and spreads it across different availability zones. And if one of those replicas goes down, there'll be no visibility into that for your application. It's also strongly consistent. It can scale to petabytes of data through horizontal scaling. If you need more data storage, all you have to do is add in another node, and the system will do the rest. It also has automated backups built in. And finally, we have our third type of node, which are our PD nodes. And this is our cluster management nodes. And these nodes function just like a full-time database administrator. It stores metadata, it coordinates data distribution, it coordinates replicas, and it'll also coordinate self-healing. If it notices one replica went down, it'll regenerate that replica all automatically and without any manual intervention. Now, let's talk about TiDB's strengths and weaknesses. TiDB is typically very fast, but it doesn't achieve the same level of latency that you might get from a single instance writer like Aurora. And this is because it has to wait for confirmation from replicas on other nodes before it can issue a response to a query. Through this, it's able to maintain strong consistency across the cluster, but it does slow down transactions a bit. And due to the nature of the speed of light, unfortunately, there's no way around it. So that's going to exist in every strongly consistent distributed system. In the scale section, this is actually where TiDB really shines. It doesn't have fives across the board, which I pretty much reserved for your data warehouses, which can have hundreds of petabytes of data, but it can scale to that low petabyte range, which puts it far ahead of the overwhelming majority of databases. On the transactions front, TiDB scores fives across the board, maintaining full ACID compliance across the cluster without caveats. In the function section, TiDB excels past actually what you would expect from a relational database, particularly in query complexity. And this is due to TiDB offering a columnar extension node for analytical queries. So we can handle those complex queries much better than a typical SQL data or a database. It also excels in the schema flexibility category due to TiDB allowing for things like online DDL, which you perform without having a noticeable performance impact on the system. So it's a very flexible schema. All right, jumping into TiDB's fit. Now, when should you use TiDB for your application? If you have data sizes in the medium to large range, so 5 terabytes to 1 petabyte, that's kind of TiDB's sweet spot. If you have a high read and write concurrency, anywhere between 50 to 1 million QPS, if you have needs for millions of different tables and schemas, TiDB has excellent support for many different schemas and tables, all in a single cluster. If you need MySQL support with some added horizontal scalability, or there's a critical need for high availability in the system, if you need strong ACID compliance across an entire cluster, or you have a hybrid transactional and analytical workload, TiDB can provide a single view of your data while servicing both types of queries. Or if you have frequent schema changes in DDL, but you still want the benefits of a typical relational database. Now, what are the bad fits for TiDB? I would say number one, small scale applications where a lightweight single writer database will suffice. TiDB will introduce complications if you, in the sense that anytime you're handling a multi-node system, there's going to be a little bit of overhead that goes along with that. Now, TiDB is much less overhead than pretty much any other system, but it's still going to be more overhead. And if you can get away with using having a single MySQL instance or a single Aurora instance, that actually might be a better fit than moving to TiDB, and then maybe moving to TiDB after you get up to the point where you have to shard. If you need single node level performance on reads and writes, if to you a few milliseconds really matters, if 2 or 3 milliseconds actually makes a massive impact on your application, sticking with those single node writer databases might be a better fit. Now let's compare. Now that we've kind of analyzed both databases, let's quickly compare the features of both databases. So on the online front, the latency front, Aurora wins out. Its latency is going to be faster than TiDB typically. On the scale front of things, this is kind of where TiDB shines. And so TiDB is definitely looking a lot better in this category. The transactional category, it's pretty much even across the board. And in the function category, TiDB is better with query complexity and schema flexibility. And I think this is actually largely due because Amazon Aurora is part of the Aurora ecosystem. And so it doesn't try to do anything. It doesn't try to do anything beyond its scope, because Amazon has other tools that you would use for highly complex queries, or if you need a very flexible schema. All right, so now that we've kind of done this full comparison, I would just like to go over a couple case studies that compare people's experiences on Aurora and as well as their corresponding migration to TiDB. So Plaid, if you're not familiar with them, is a multi-billion-dollar financial technology company that connects users' bank accounts to financial applications. They power over 500 million financial transactions per day, which is 25% of the transactions in all the United States. And they actually they were on Aurora for a long time, but they had quite a bit of issues with it. Number one, they had downtime. They had some downtime in 2022, which caused major revenue loss. And they had situations where potential customers were declining to do business with them because they were seen as unreliable. They tried to fix this through an initiative, but they were unable to eliminate any downtime on Aurora. And I think that this is just the nature of having 270 separate clusters on Aurora. I mean, the probability of a node failure just goes up exponentially at that scale. There was also in a situation where Aurora was going to force them to do an upgrade from 5.7 to 8.0, which would take them 9 to 12 months to complete, because you're doing this upgrade on 270 different clusters of Aurora. They migrated to TiDB, and TiDB was tested and proved to be far more reliable than Aurora in the POC. And they had a 20% reduction in manpower. There was no forced downtime with online schema changes and rolling upgrades, some of the features of TiDB. And the result was that they consolidated those 270 clusters of Aurora into 4 TiDB clusters, significantly reducing their costs. And before I fully wrap up, I'd like to talk about TiDB on Flipkart, because I think this is very interesting, just give you an idea of the scale that we're talking about here. So Flipkart is the Amazon of India, and they do over 1 million consistent reads on TiDB at 7.43 P99 and over 123,000 writes at 13.1 P99 milliseconds. So very fast and at massive scale. So who is PingCap? Who are we? So we're the company behind TiDB. We provide enterprise level support, cloud-based services, and we support open source deployments, self-hosted deployments, fully managed deployments. We've been around since 2015, and we have over 550 employees globally.